Yes.
Okay. So today we are doing thermal expansion. Today we are taking thermal expansion. Okay. Now, first of all, what is expansion? Metals they can also expand. Solid expand, despite the particles that makes them up tightly put together, but still they can expand. What will result to that? What leads to the process or the situation whereby solid begins to expand? That happens when you heat them. So when you heat a solid or any material generally, when you heat them, they can expand. When you heat any material, that material is subjected to expansion. Now, why does that have to be like that? Why do they have to expand when you heat them? This is because the molecules start to move around. When you heat, let's take solid for example, for instance, when you heat a solid, they will begin to vibrate. The particles will begin to vibrate, meaning they will begin to like be shaking and be moving. They will start to move. They will start to move. They start to vibrate. They start to move around, and they will do this faster as the temperature increases. They will move faster or they will vibrate faster. And what happens is that at the end of the day, it will cause them to knock each other off and push each other apart. They will knock each other off and they will push each other apart. Is that okay? Now, this is it from the diagram. Take a look at what we're saying from the diagram. These are particles in a solid or in any given material. Let's say solid practically. So when you heat them, they will begin to shake and they will begin to like move in different direction. They'll begin to move in different direction. They'll begin to disagree, the bond holding them together will begin to loosen, will begin to be broken. And then this particle obviously and outrightly begins to take effect, like the bond holding them together begins to break, begin to loosen, and this particle begin to feel the need to move, pull away from each other. The energy you supply, the heat energy you have supplied, makes them feel enemy to one another. They were very comfortable. They were in their comfort zone, the particles. They were being held together by strong forces, maybe strong van der Waals forces or strong intermolecular forces. So the bond holding them together usually is very strong. So when you heat, this force or this bond holding them together begin to break loose. And when that happens, they start to pull apart from one another. When they pull it apart from one another, they're expanding. They're getting bigger. They're getting increased. Because it is the particle. When the particle are expanding or when they get pulling apart from each other, then they are expanding. Expansion is taking place. So this small diagram you see is when a solid is heated. It's a diagram showing the condition of a solid when it's heated. We say when it's heated, the molecules vibrate even more and push each other apart. And such leads to what we call expansion. Is that okay? Now, one thing you need to take note of is that when this happens, it causes a space between them, between the molecules. The space between the molecules increases. So hence, they will expand. The molecules themselves remain the same size. The molecules do not increase. The size of the molecule do not increase. They remain the same size, but a bigger space begins to happen between them. So the expansion does not mean that the molecule increases size. No. It only shows that the spaces between the molecule increases. The spaces between the molecule increases. Are we together? The spaces between the molecule increases. So when heat is supplied to solid, the molecule vibrates and pull each other apart. Hence, the spaces between the molecule increases, but not the size of the particles. the size of the particles or the molecules do not increase. The size of the molecule do not increase, but the spaces between the molecule increases. So that leads to what we call expansion. Thermal expansion occurs in solid, not only solid, also occurs in liquid and gases. So whether you heat a solid, it can increase. You heat a liquid, it can increase. And you heat a gas, so it also increases. When temperature is increased at constant pressure, when you increase your temperature and the pressure is same, solid will tend to expand at the least. They will tend to expand the least because the forces holding them together is stronger. Okay, so solid tends to expand the least because it takes a longer time for solid to actually begin to expand, especially metals. It takes a longer time and higher temperature to actually cause solids to practically increase or to expand. So unlike water, within a few minutes, you can expand a liquid. Within a few minutes or seconds, you can expand gas. Gas expands the most at a given temperature. If you give equal temperature to solid, liquid, and gas, the gas will expand the most. Gas expand the most. Okay? Solid expand the least. Solid is the least in expansion because solids are hard. The molecules are bonded together very strongly with high van der Waals forces or high intermolecular forces, and it takes a very high amount of temperature to break loose this force to create space between molecules of solids. Now let's take a look at thermal expansion in terms of particles. Let's take a look at expansion in terms of particles. We say molecules do not expand, but the spaces in between them does. Not the molecules. The molecules do not get more. The number do not increase. The size do not get bigger. The size of molecules do not get bigger. The number of molecules do not double. Then what causes the expansion? What is the expansion all about? So when we say expansion, expansion is actually increase in length, increase in width, increase in height. If it has to do volume expansion, if it has something to do with a volume expansion or volume expansivity, which you're going to do in a bit of higher level, you'll be talking about increase in length, increase in width, and increase in the height. But if you're talking about area expansion, which is called superficial expansion, you're talking only about increase in length and increase in width of that concept, of that material. If you're talking about only linear expansion, you're only talking about increase in length. If we're talking about linear expansion, we're only talking about increase in length. Is that okay? So molecules do not expand. The molecules themselves do not expand, but the space between them is what expands, what gets bigger. Meaning they pull apart more from each other, from one another. The molecule pulls apart more from one another. The expansion we are saying is that molecules get away from each other, create a longer or a bigger space between one another. And when that happens, we say the materials or the substance have or has expanded. Is that okay? When solid or liquid or gases are heated, we get the following. Now let's take a look at them, the different states. Solid, for solid, the expansion, they expand slightly. Like we said earlier, it takes a lot of temperature to cause serious expansion to solid. Because take, for instance, metals, iron, steel, these materials are very hard. So you don't just apply small heat and then you think they will expand. No, if you have a cutlass, think of any metal you have with you, metallic substance. If you have any metallic substance, the body of a car, just think of any metallic substance. Okay, your shower, if it's made of metal. If you want it to expand, you just supply a little heat, it will expand? No. Hell no. If you want a solid to expand, you go to heat it to a very high temperature. So in other words, if you give them equal amount of temperature, solid, liquid, and gas, solid will be the one that expands the least, because it takes a very high temperature for the molecules to actually break loose. and begin to get away from each other. So we say solid, they expand slightly. They expand very slightly, not so much compared to others. Due to what? The strong bond holding the molecules together. I already explained this. Due to the strong bond holding the molecules together. That's why their expansion is very slightly, very little. The least is the least, okay, in expansion. Now let's take a look at liquid. Liquid expand more than solid, but less than gas. They expand more than solid. Why? Due to the weaker bond that's holding the molecules together. The molecules in liquids, the bond holding them together is a bit weaker than that of solid. So it will definitely expand a bit more than that of solid, right? Since the bond holding them together is weaker than that of solid. Now, in the case of gas, the gas, they expand the most, and they expand very significantly, very prominently. So why is this so? Due to there being no bond holding the molecules together, little or nothing. Okay, due to the fact that there could be no bond holding the molecules together. Is that okay? So that's that for that. Let's take a look at the uses and consequences of expansions. This one normally comes in the exam. Please pay attention. It comes in the exam. So uses and consequences of thermal expansion. What do we use expansion? Expansion has benefit, and it has a bad side. It has a disadvantage. This is like advantages and disadvantages of thermal expansion. So when we say uses and consequences of thermal expansion, it's like we are saying the advantages and disadvantages of thermal expansion. That's the meaning. It's like you're saying merit, the merit and demerit of thermal expansion. That's the meaning. Is that okay? It's like we're saying the merit and the demerit of thermal expansion. So now or you're saying the application and consequences. Application is like the uses, the benefit, the good side of expansion. The good things that we get from expansion. That's also called application or advantages or merit or uses. So no matter the language they use in your exam, you should understand their concept, and you should understand that it means the applications, or it means the advantages, or it means the usefulness, or it means the benefit from thermal expansion. Let's take a look at the merit first, or the benefit, or the application. Before we talk about that, let's itemize this. So the thermal expansions of material can have some useful application and also have some undesirable consequences. When we say consequences, we are talking about the disadvantage, the bad effect, the negative effect, or negative impact. So when we say about the consequences, we are talking about the negative impact, the negative impact, the bad impact, the disadvantages, the demerit. That's what we mean by the consequences. Now we understood these two concepts. Now let's take a look at the advantages, or what you call the application, or the usefulness, or the merit, or the benefit, or the positive impact. Now let's take a look at that. Number one is that we say the thermometer rely on the expansion of liquid to measure temperature. The thermometer, they normally rely on the expansion of liquid inside them for accurate measurement of temperature. For accurate measurement of temperature. Why is that so? You know, we have different types of thermometer, which we're going to study later on. We have the liquid in glass thermometer. The liquid in glass thermometer, you know, they operate with a liquid inside them. They operate with a liquid, either mercury as a liquid or alcohol as a liquid. But normally we prefer mercury as a thermometric liquid because of its ability to quickly expand when heated. Ability to quickly expand when heated, and it's colored, and so you can easily see the graduations, the calibrations on the thermometer. You can easily see the calibration because it's colored. Alcohol and the glass itself, the thermometric glass, looks same. So when you use alcohol as a thermometric liquid, it's difficult to read it. It's difficult to see where the alcohol has flown to, because the color of the alcohol and the color of the glass of the meniscus that the thermometer is made of, they're same. And again, mercury expands more quickly or more than alcohol. Mercury can expand quickly more than alcohol. Now let's so in thermometric liquid, or when you take a thermometer like the clinical thermometer or the laboratory thermometer, they use thermometric liquid like mercury and alcohol. Now this liquid, they have to expand. They expand when you use it to touch, when they're heated. When you use it to touch our body is, our body is normally hot or a bit warm. When you touch them, they can sense the heat from the body temperature, and the liquid quickly get expanded, and then they can flow. This liquid can expand. So we are saying that thermometer, they rely on the expansion of the liquid to measure the temperature. The liquid inside them, the mercury liquid, they have to expand in order for them to be able to measure the temperature of the body or of the substance that you're measuring. That's number one application. So number one application is that expansion helps us to take accurate measurement of temperature. That's number one. Number two is that temperature activated switches work when a biometric strip consisting of two metals that expand at different rate bends by a predictable amount at a given temperature. A biometric strip. This is a good example. Let's take a look at the diagram. Let's take a look at this diagram. It's a biometric strip, bimetallic strip. This bimetallic, bi means two, means it's made up of two metals. One is up, you can see a different color, like orange color, and then there's a blue color at the bottom. So what this signifies is that it's made up of two metals. One is up, one is on top, the other one is the bottom. When you supply heat, this metal will bend towards the one that expands the most. These two metals, they expand differently. So maybe the orange one expands the most, so it bends towards that one. So when it bends towards it, it can touch the contact. So then the circuit will be on. So it's used for actuating and activating a circuit. A bimetallic strip is used for activating a circuit. So when you supply heat a little bit, these two metals will expand, and it will expand towards the one that expands the most out of these two. The expansion is not the same because they are not made up of the same. Maybe one is iron, one is EVA as a metal, the other one could be a steel or an iron or a bronze. So one expands more than the other one. So when you supply heat, then the one that expands the most is on top, and then it's able to bend and touch this contact, then the circuit will on. This is a broken circuit, the circuit that is not on. So when it expands and this edge touches this place, then the circuit will be on. So it can be used for switching. It's used for switch, as a switch. So expansion helps us to be able to operate switches in a dangerous location. So you can put it in that singular way. Expansion helps us to operate switch in dangerous locations. Switches that we cannot go and touch. We cannot on and off. The switch in your house, you can just touch it by owning it, switch it on, switch it off. But there are some dangerous locations in the industrial application where you cannot go and touch the switch. So we use the expansion to put the switch on and off. When you want to put it off, you stop heating it, and then after a while, it will lose contact with this contact and then pull off, and then the whole circuit will stop. Okay? There are other benefits which we might talk about. It's not just limited to these two. So there are other applications of expansion. Expansion is not just limited to these two scenarios. Okay? There are other applications of expansion. Okay? Any idea? This is the thermometer, and this is bimetallic strip. How it bends helps to switch off a dangerous circuit. Right? Okay, here now we'll talk about the consequences. Okay, and then another application is that expansion gaps are allowed in bridges. You know, when you're climbing on a bridge, when the roads, you see that we allow gaps, and these gaps are made up of metals. So when you climb on the bridge, you see that you start making boogum, 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 boogum. Not the negative boogum like as if it's a pothole. You feel the metallic on the road, right? So these are to make the road or the bridge last longer. This is to make the bridge last make the bridge last longer. That's why we allow gaps. So gaps are provided in order to create this thing on the road and bridges. I think this is a consequence anyway. Now let's take a look at the consequences. Let's take a look at the consequences. That means the disadvantages of expansion. Number one, we say the expansion of solid material can cause them to buckle if they get too hot. Yeah, if you heat solid too hot, if you heat solid material too much, they will buckle. They will slack. Okay? Now this could include metal railway tracks. You know the railway, the train, we always use train, right? The track where the train follow, you know they are made up of metals. So when they are heated too much, they will slack. It will affect the railway tracks. So the government have to fix. They have to fix when the tracks get slacked or buckled. That's one negative effect of expansion. It causes the railway tracks to buckle. That's number one. When the expansion is too much. Number two, the road surfaces. The road surface will easily wear off due to heat. They will wear off, they will spoil. The road will spoil. They will crack. The road will crack due to heat from the sun hitting it every time. The road will crack. Okay? The coal tar, you know they used the bitumen to make the road and the gravel and all of this stuff. So the heat will crack the road, will buckle the road, will slack the road, and will break the road eventually. So this is another negative effect of expansion. Then the bridges, it will cause bridges to slack or slide or buckle or and so on and so forth. So these are three big consequences of expansion. It affects our railway track, it affects our road, and it affects our bridges. Things that are prone to buckling in this way, they have gap built in. If you want them to last long, what do? You put gaps between them. You put gaps between bridges. You put gaps on the road. You also put metallic disc to allow expansion. You put gaps on the road with metals to allow expansion. When the road expands, you create allowance for them so that the road do not get destroyed so easily. This will create space for the expansion to happen without causing damage to the road or the rail or the bridge. Thermal properties and temperature. Let's take a look at this question.
It's a video.
Okay. So one of the exam tips to remember is that material that expand, not the molecule, is material that expand. The spaces expand, not the molecules. So you should remember this in the exam. When heat is added, then temperature will increase, and it will lead to increase in kinetic energy, so that the molecules and the atoms will move quickly apart from each other. Okay? This separation of the molecules makes the substance to get bigger. So let's go to the next one. Now this second one is the heat capacity, specific heat capacity. specific heat capacity. Let's quickly take a look at this section. Is that okay? Or should we do this one in another class? Huh?
It's 10:15.
Oh, we stay after. Let's move up quickly. Specific heat capacity. Thermal capacity or specific heat capacity is just the energy that is required to cause maybe an increase in temperature. The energy required to cause increase in temperature, to cause the substance to rise, the temperature to rise. Now let's talk about the internal energy. The internal energy first. You know, every material has its own internal energy. Now, a rise in the temperature of an object increases its internal energy. What it means is that when we keep increasing the temperature, then we are increasing the internal energy. Because energy is a function of temperature. The internal energy is a function of temperature. You increase the temperature, then you are increasing the internal energy of the substance of the material. So, if you're looking at this, you look at it due to the increase in the average speed of the particles, in terms of the average speed of the particle. Because when you increase temperature, the speed of the particle will increase, right? The speed of the particles will increase. The speed of the particles will increase. So when the speed increases, then increasing the speed will increase the kinetic energy. Increasing speed increases the kinetic energy. Remember the formula for kinetic energy. Let's remember the formula for kinetic energy. Kinetic energy, let me write KE. Kinetic energy is equal to half mv squared. Half mv squared. Okay? Where m is equal to the mass of the substance or of the molecule. The mass. M is equal to the mass. And V is the speed. You can use it for speed, you can use it for velocity. V is the speed. So when you increase temperature of a substance, the speed will increase because the molecule will start to move faster. The molecule will start to move faster. When you increase the temperature of a substance or of molecule, when you increase temperature, the speed will increase. The speed will increase. Once the speed increases, then the average kinetic energy will increase. You know why? Because speed is a function of kinetic energy. Look at it, V. V is directly proportional to KE. KE is the kinetic energy. KE is the kinetic energy. Both the kinetic energy and the speed are directly proportional to each other. What that means is that when one increases, the other one will also increase. See? Kinetic energy and speed are directly proportional in this formula. So what that means is that when the speed increases, then the average kinetic energy will also increase. The average kinetic energy will also increase. The average kinetic energy will also increase. So once the kinetic energy increases, then the molecule will expand or okay. So K is the kinetic energy. So you can see that the kinetic energy KE, the kinetic energy is directly proportional to the speed. Speed is is the V. It's directly proportional to the V. So remember the formula for kinetic energy. We've done this in the work energy and power. When we did the chapter of work energy and power, we studied the kinetic energy. So the kinetic energy is half mv squared, half 1/2 times the mass times the speed square of the speed, times the square of the speed. So we say this speed is directly proportional to the kinetic energy. So when you increase the speed of the molecules, then the molecule will gain more kinetic energy. The meaning kinetic energy of the molecules will increase. The kinetic energy of the molecules will increase. So once that happens, then we are good to have expansion, or we are good to have expansion, and we are good to have an increased internal energy. We are good to have what we call increased internal energy. Now let's define the internal energy. The internal energy is defined as the total energy, okay? It's defined as the total energy inside the system by the particle that makes up the system due to their motions and their position. Just internal energy is simply the total energy. The total energy inside a particle. The total energy inside a system by the particle. The total energy inside a system by the particle. Meaning this energy is contributed by the particles inside the system. For example, the total energy inside your stomach now. The total energy inside your animatric canal. Let me not say stomach. Stomach is just a part of the animatric canal. The total energy inside your animatric canal will be made up by all the organs in the animatric canal, including the esophagus, the mouth, the esophagus, the stomach, the small intestine, the pancreas, the liver, the bladder, everything that makes it up, the small intestine, the large intestine, all the energies from these particles. So we consider each of these as a particle. For instance, we consider each of these as a particle. So the total energy in a system, stored inside a system, the internal energy is defined as the total energy that is stored inside the system. The internal energy is defined as the total energy that is stored inside the system by the particles that makes up that system due to their motions and their position. Due to their motion, whether they are moving, or due to their position, whether they are in a fixed place, in a fixed point. Meaning, in other words, the internal energy is the total energy which technically means the potential energy and the kinetic energy inside the system. Which technically means the potential energy and the kinetic energy inside the system. The kinetic energy is the energy it has during motion. The system has during motion. And the potential energy is the energy it has when it's in a fixed position, when it's in a position. Okay? So when we're talking about the internal energy, we are indirectly talking about the kinetic energy plus the potential energy. So in other words, we call it total energy because you add the two energies together. So we're saying that the internal energy is the total energy stored in a system, stored inside a system. What are these energy? Both the potential energy and the kinetic energy. So it's the total energy stored in the system by the particles that makes up the system. Okay? And due to the motion and position of that system. So I think by now we understand what is internal energy. It's always the total energy, both the kinetic energy and potential energy inside the system as a result of the particle of the system. Motion of the particle affects their kinetic energy. Yes. If it's moving slowly, it has more kinetic energy. If it's moving faster, if the particles are moving randomly and faster, they have more kinetic energy. Now, regarding the position of the particle related to each other affects their potential energy. When they are in a fixed position, then they have what we call the potential energy. When they are moving, they have what we call the kinetic energy. So when you talk about internal energy, you are talking about the sum of the potential energy and the kinetic energy inside the system. So you can also define internal energy in this manner. You can say the internal energy is the sum of the potential energy and the kinetic energy inside the system. The sum of the potential energy and the kinetic energy inside the system. So you can define the potential energy and the internal energy as the sum of the potential energy and the kinetic energy inside the system. Or you can simply say the total energy The total energy stored in a system by the particles that makes up the system, both due to motions and due to their position. Motion means when they are moving, position means when they are in a fixed point. Okay, now let's take a look at the arrow one is called the kinetic energy. Look at these particles inside this container. Take a look at the particles. The particles are colored blue or blue, right? Huh?
Yeah.
So the particles are colored blue, but they have arrow. The arrow shows that they are moving. They have black arrows. The arrow, this is not green arrow. There's a movie called green arrow, right? Okay, this is not green arrow. This is a black arrow. The arrow shows that they are moving, and once they are moving means they have kinetic energy. And then the red shows potential energy. Red shows they are in fixed position. This one is showing the relative position of the two particles. This one in a fixed position relative to this one in this position. This one is this position relative to this one in this fixed position. This one is in fixed position relative to this one in a fixed position. So it's looking at the red is showing their relativity in fixed position. At that point, they have potential energy when they are in fixed position. Is that okay? So let's move on quickly for the sake of time. Substances, this figure is showing substances have eternal energy due to motions of the particles and due to their position relative to each other. So they have potential energy due to their position relative to each other, and they have kinetic energy due to their motion. Now let's talk about the average kinetic energy. This one is really for the exam students, the IGCSE exam students. Now we say when you heat a system changes a substance internal energy by either increasing by seriously increasing the kinetic energy of its particle. So when you're heating a system, you are increasing the kinetic energy. How? When you heat a system, the temperature increases, and when temperature increases, it's going to increase the speed by which the particles start to vibrate or start to move away from each other. So when the speed increases, then they will gain kinetic energy. When speed increases, they gain kinetic energy. Now they gain so many different kinetic energy. You know, it's not just one particle or one molecule. It's not just one molecule. It's made up of several molecules. Made up of several molecules in a system or in a container. So when you heat a container, the container is not made up of one molecule alone. It's made up of several molecules. So we'll be talking in terms of average now, because each of them each of the molecule will gain heat. Each of the molecule will gain heat, and that heat will increase their speed of movement. So now this will automatically lead to kinetic energy because they will be in motion. When they gain heat, then they start to experience speed. When the molecules are experiencing speed, then they are in motion already. Because when you have speed, you are in motion already. Now, it's not just one molecule. It's made up of several molecules. Right? It's made up of several molecules. 1, 2, 3, no. Made up of several molecules. Made up of several molecules. Okay? So, in this manner, we'll be talking about the average kinetic energy. Average. We cannot be talking about the energy of one, the energy of the other one, the energy of the other. So, let's talk about their average energy. Meaning, sum them up and divide by the number of molecules you have. So, in terms of average. So, we talk about the average kinetic energy of the molecules. Temperature increase, temperature, it will increase the average kinetic energy of the molecules. Now, this increase in the kinetic energy, which eventually leads to an increase in the internal energy, can be caused by or can cause. Now, let's take a look at the effect. What happens when we increase the kinetic energy? Automatically, the internal energy will also increase. When we increase the kinetic energy is increased as a result of the fact that we increase the temperature. When you increase temperature, the molecules gain speed. They start to move. They gain speed. Now, because it's more than one molecule, we now talk about their average speed. Now, this average speed will lead to average kinetic energy. Because when you are moving, you gain kinetic energy. When you start to move, you gain kinetic energy. So the average kinetic energy will cause the following. One, will cause the temperature of the system to increase. An increased energy, or an increase, the increase in kinetic energy, which is also an increase in the internal energy, is caused by the fact that the temperature of the system has increased, or we cause the temperature of the system to increase, or we produce a change of state. If you're a solid before, you can melt and become a liquid, and if you're a liquid, you can boil and become a gas. So it will cause or produce what we call a change of state. Because yes, obviously, if you keep heating a substance, let's take ice for instance, if you keep heating an ice, it will melt and become liquid, right? And then if you keep heating the liquid, it will boil and start to evaporate, right? And become a gas, become water vapor, become a gas. You see steam trying to escape from your cover pot, from your pot cover, trying to push the pot cover up. Those you see, they are called steam or water vapor. They are gas. They're called the gas. Okay, normal gas at low temperature. Excuse me. Yeah, here you see normal gas at low temperature, and you see heated gas at high temperature. Now let's take a look at normal gas at low temperature. The gas molecules are free to move and have no intermolecular forces. The molecules, even normal temperature, normal gas at low temperature, the molecules are able to move and they do not have intermolecular forces that is holding them together. The gas do not have intermolecular forces that is holding them together, holding the molecules together. Now when you heat the gas, what happens? The gas molecule move much faster with higher kinetic energy. When you heat them, the molecule move much faster compared to this one. These ones, they move much faster, okay, with higher kinetic energy. Because when you heat them, they gain more kinetic energy, and they can move much faster. You can see the heat concept being provided to this. This is a Bunsen burner, which heats up this container. Okay, the molecules have more internal energy now because they can move rapidly. They can move absolutely. They can move rapidly, and they gain more kinetic energy. On the other hand, the first one is not supplied with heat, so they do not gain increased internal energy or increase kinetic energy. Now let's take a look at specific heat capacity. Let's take a look at the concept of specific heat capacity. How much of temperature of a system increases depend on the following concept. How much amount of temperature of a system increase depends on the following. Okay? How much temperature increase of a system depends on the following. One, let's take a look at the factors. One, the mass of the substance. If the mass is small, it's very easy for the temperature to increase when you supply heat. It's very easy for the temperature to increase. If the mass of a substance is very huge, it takes a bit of a while, okay, for the temperature to increase, even if you supply heat. Is that okay? That is an understandable concept. Then also another factor upon which this depends is the nature of the material. If you take ice, for example, you heat an ice, within a few minutes, between 1 to 5 minutes, the ice will start to melt, right? Or like you take a metal, like an iron or a steel, you put it in this thing and start to heat it. It's going to take donkey temperature to melt it, right? So that's what we mean by nature of material. Even among solids or among metals, metals are stronger than each other. If you bring a steel which is an alloy of a metal, like 3 metals put together. Steel is an alloy. It consists of iron and other metals, right? So steel is stronger than iron itself. So it will take a longer time for steel to melt than iron to melt, right? So this is what we're saying. The melting point of steel is higher than the melting point of iron, or the boiling point of steel is higher than the boiling point of iron. So you can see the nature of materials determines how far the temperature will increase, even if you supply heat. Even if we supply heat, the nature of material, as we've explained, determines one of the determinants of how much heat energy or how far the temperature will increase. Another factor that determines how the temperature will increase in a system is the amount of thermal energy transferred into the system. The amount of thermal energy that is transferred into the system. So even if you heat something, if the energy that you supply is being lost or is escaping, maybe not much is entering the system. Maybe not much of the energy that you are supplying or heat that you are supplying, not much is entering the system. So how much enters into it also is a factor. It's also a big, huge factor that determines how much temperature increase that the system will get, how much of increase in temperature the system will get. Now, from these 3 factors, we're able to derive what the specific heat capacity is. So here and now, we define the specific heat capacity of a substance as the amount of energy that is required to raise the temperature of 1 kg of a substance. You see, we mention 1 kg because we want to let you know 1 kilogram mass. We are measuring the mass. The specific heat capacity of a substance is defined as the amount of energy required to raise the temperature of 1 kg. You must mention this. 1 kg of a substance by 1 degree Celsius. So you must measure these 2 things. Okay? Now, let me break this down for you so that you get this concept. Let's say you take an ice, you're heating an ice. Now, the amount of energy, heat energy, that is required for just 1 kilogram of it, not the whole ice. 1 kilogram of it to increase its temperature by 1 degree. Let's say the temperature of the ice was 0 degree or minus 1 degree. Let's say the temperature was minus 5 degree. Now, if it increased by 1 degree to become minus 4, you know negative numbers, when they increase, they become smaller. When they decrease, they become bigger. For negative number. Do you understand, right?
Yes.
So when you say it increased by 1 degree Celsius, from minus 5, it will become what? Minus 4. When it decreased, it becomes minus 6. Okay, let me use it from positive number. If it was 1 degree before, if it increased through 1 kg of a substance, was 2 degrees before, let's say 1 kg of a substance, 1 kg of an ice, we're looking at 1 kilogram. 1 kilogram of ice. 1 kg is a bit big, right? When you weigh it. 1 kilogram of ice, if you put it, how much heat energy can cause it to increase its temperature from maybe from 2 degrees Celsius to 3 degrees? To increase just through 1 degree Celsius. 2 to 3 means 1 increase through 1, right? If or from 0 degrees Celsius to 1 degree Celsius, that's increased by 1 degree Celsius. From 0 to 1 is increased by 1, right? So, and if you take 1 kg and the substance can increase through 1 degree Celsius, the substance can increase through 1 degree Celsius, then that heat energy that can cause that increase is called the specific heat capacity. It's called the specific heat capacity. And different substances have different specific heat capacity. Metals, different substances have different specific heat capacity. Okay? Now, if the formula that relates this, where's our okay. Let's erase this. Okay. The amount of, okay, let's take the pen now. We say the energy, the amount of energy required is equal to the mass multiplied by the specific heat. Specific heat capacity, I use C small subscript S. Then multiplied by delta T. Delta T means change in temperature. This is the energy formula. The energy required is given by this formula. Mass times specific capacity that multiplied by delta T. Now this specific capacity that we're describing, this small one, I write C. Most textbooks they write only C, but I put small s to show specific heat capacity. If you want to make it the subject, you make this one the subject, you go to say energy divided by mass and delta T. This energy divided by this mass and delta T. So this one is given us energy over mass and delta T. The product of mass and delta T. Change in temperature. Delta T means change in temperature. So if I call this one equation 1, I'll call this my equation 2. Okay? So this is the specific heat capacity. Is the energy divided by mass and the product of mass and change in temperature. Where delta T, remember, we can give equation 3. Where delta T, I know you're wondering what is delta T. Where delta T is final temperature minus initial temperature. Final temperature, let's call it TF or T2. Let's call it T2 minus initial temperature, which is T1. Initial temperature, which is T1. Minus initial temperature, which is T1. So let's call this equation 3. Okay, first and foremost, when you give a problem, you have to find delta T by saying the final temperature. If they tell you the final temperature is 70 and the initial temperature is 20, so you find change in temperature, which is called delta T, by saying 70 minus 20, which is 50. So we're going to use 50 in calculation, not 20, not 70. So you have to find the change in temperature first before you do any calculation. If they ask you to calculate the amount of energy required, then you put the specific capacity. You put the mass, you multiply by the change in temperature, you get the energy required. But if they want you to calculate the specific capacity, they will give you the energy. You say the energy divided by the product of mass and the change in temperature. Then you get this the specific heat capacity. Is that okay?
Yes.
Okay. Yes. So now let's take it. We say the specific capacity, we've defined it, right? We say is the amount of energy. Is the amount of energy required to raise the temperature of 1 kg of a substance through 1 degree Celsius. It's very easy to define. Okay? It's the amount of energy that is required. So when they ask define specific capacity, you say it's the amount of energy that is required to raise the temperature of 1 kg of a substance through 1 degree Celsius. The amount of energy that is required to raise the temperature of 1 kg of a substance through 1 degree Celsius. It's very easy to say. First, the specific capacity is the energy needed. Okay, not only required, you can use the word needed. The energy that is needed to raise the temperature of 1 kg of a substance through 1 degree Celsius. The amount of energy that is needed or that is supplied or that is required to raise the temperature of 1 kg of a substance through 1 degree Celsius. Now, let's take a look at the different substances. We say different substances, they have different specific capacity. Yes, obviously, you don't expect steel to have the same heat capacity with ice, or to have the same with iron, and so on and so forth. Now, if a substance has a low specific capacity, it heats up and cools down very, very quickly. If something has a low specific capacity, you can, when you heat it, like for example when we talk about ice and when we compare ice and steel, You can eat ice quicker. It will heat up quickly and it will cool down quickly. Right? Such substance can heat up quickly and can cool down quickly if it has low specific heat capacity. When substance has a very high specific heat capacity, it heats up and cools down slowly. Meaning it does not heat up quickly. It takes time to get heated up and it takes time to cool down. So when something has a very high specific heat capacity, it heats up and cools down slowly. It takes time. When something has a high specific heat capacity, it heats up and cools down slowly. It takes its time. Okay? It takes time, more energy to change its temperature. So it takes time. It doesn't like hurry up. Okay? Now this is a copper block. Where most stop you, okay? This is a copper block, this is aluminum block, and this is water. Copper, aluminum, and water. So now the specific heat capacity of copper is 390 joule per kilogram degree Celsius. The specific heat capacity of aluminum is 910 joule per kilogram degree Celsius. Per degree Celsius. The specific capacity of water is 4,200 joule per kilogram per degree Celsius. So now here I will declare to you that water has very high specific heat capacity. Water has a very high specific heat capacity. And the value is, you need to know it. Because most times they will not measure it for you in a question, but they will tell you the substance is water. It's a constant value. It's very unique and you need to know it. It's 4,200 joule per kilogram per Celsius. Okay? So you can see in this case, water has a higher specific capacity compared to these two. Aluminium is even higher than that of aluminum and is higher than that of copper block. Now, the lower specific heat capacity warms up and cools down quickly as it takes much less energy to change its temperature. While the higher specific capacity warms up and cools down slowly as it takes much energy to do this. Now we've given this formula, but in this text they use, I use E here, but they use Q to represent the energy. They use Q to represent the energy, but just now when I was showing you on this board, I use E, delta E. Even the energy you can use delta E, meaning change in energy. Okay? Change in energy. Means change in energy. Okay, but in this text, they are using, some textbook they use E for energy, and some textbook they use Q. So don't be surprised or don't be confused. It's the same concept. Is that okay? But I stick to E to make it easy to remember that it means energy. Q could mean any other thing. So easily we can remember it means energy. So the change in energy, the amount of energy needed to raise the temperature of a substance or the mass of a substance can be calculated using this formula. Delta Q or delta E is equals to mass times C. You know, I told you in textbook they just use C, but for me, I put small subscript S to show that it's specific heat capacity. And delta T. Delta T is change in temperature. So they define their parameters, you see, just like the way we defined ours. Delta Q, they call it change in the thermal energy. Okay, because they use it thermal, the word thermal. So that's probably why they use Q in joules. The unit of this energy is in joules. And then the M is the mass in kilogram, and C is the specific capacity in joule per kilogram per degree Celsius. And then delta T is change in temperature in degrees Celsius. Now here comes a question. We go to calculate. Although they've done it, but we do it in our old whiteboard. Okay? Let's do it in our old board and see if we're going to get it. Now it's a water of mass 0.48 kilogram is increased in temperature by is increased in temperature by 0.7 degrees Celsius. Meaning this is already change in temperature. They didn't tell you the initial temperature or the final. They just give you the change in temperature straight away. Now the specific capacity is 4,200 kilo. Calculate the amount of thermal energy that is transferred to the water. So if you want to do this, let's come here. This one got increased. Okay. Okay, let's clean. Let's erase. Go to the eraser. Okay. So we already know change in energy. They ask us to calculate, right? The energy, the thermal energy that is required is equal to the mass times the specific capacity times the change in temperature. So sometimes you can give the parameter. You can say the mass is given, M is what? 0.48, right? Kilogram. M was given as 0.48. 0.48 kilogram. Okay, specific capacity of water is what? 4,200. Even if they don't give you this, once they mention water, you should know this. 4,200. 4,200 joule per kilogram. Joule per kilogram. Joule per kilogram per degree Celsius. Joule per kilogram per degree Celsius. And then delta T was 0.7. So if you are looking for the energy, you just put this 0.7 degrees Celsius. So just put all of them here. So multiply. You say 0.48, 0.48, or we do it here, right? 0.48 times 4,200 times 4,200 times 0.7. So what do we get? For the energy, delta E. What do we get? Multiply. Press your calculator.
Okay.
So we get 1,400, right? 411.2. Okay, you have to put joules, the unit of energy. You put joules. Okay, so that's it. That's what we get. Is that okay?
Yes.
Okay, so that's that for this question. So I think this is the end of this section. And next one we will start from this one. Take note. Investigative specific capacity. We're going to carry out the investigation. Okay?
2.23.
2.23. Okay, so with this we come to the end of today's class. Thank you.